Hello, everyone. Thank you for joining our webinar today. My name is Carrie Williams, and I am the Director of Marketing for Test Oil. I'm pleased to be hosting this webinar today. Before we get started, there's a few things that I need to share with you. The first thing I want to do is check my audio. I want to make sure everyone can hear me. So do me a favor, if you can hear my voice, will you click on the hand icon that is in the GoToMeeting toolbar application, and that will let me know. Oh, I see some hands. So that lets me know that you can hear me. I can't hear you, and the reason why is I have everybody on mute today. We have more than 100 people registered for this webinar, and as I mentioned in the invitation that you probably received about the webinar, we are recording it. So it's best for me to keep the quality of the recording good by keeping you all mute. I understand that that kind of takes you out of being interactive with us, so I have a workaround. If you do have questions during the presentation, on that same toolbar where you click to raise your hand, just below it there is a section called Questions. You can type questions in there, and if I get a chance during the webinar, I will try to get our presenter to answer them, but most of the time we keep our questions to the end of the presentation. Now there's also a time constraint. We kind of try not to make these presentations too long, so if we run out of time, your questions will certainly be answered via email by our presenter. So with all that taken care of, let's get started. The webinar today is the reactive nature of oil degradation products. So if you are not signed up for this webinar, you're in the wrong place. It's like the flight attendants say, you're on the wrong flight. But hopefully you're on the right webinar. And our presenter today is Greg Livingstone of Fluitec. I've known Greg for many years, and we're very pleased to have him as a guest presenter. He's also presented for us many times over the last few years, so we're really pleased to have him. Just a little bit of information about Greg. He's been involved with lubrication, contamination control, and condition monitoring for pretty much his entire year. He is a CLS certified and has held industry leadership roles in several committees, including ASTM and STLE. He's also a published author and speaks at many of our industry functions, including conferences and workshops for many of the different organizations that put on conferences for our industry. So with that, I'm going to head over to Greg and let him take controls. Are you ready, Greg?
Wonderful. Okay, I am indeed. Thanks so much for the introduction, Carrie. I appreciate that. Are you able to see my screen just fine?
I can see you, yes.
Great. Okay, excellent. Well, again, the topic today is the reactive nature of oil degradation products, and so this is I think, I hope that you will find this to be a fairly interesting discussion today. But to just start off, the hypothesis that I am proposing here in this presentation is that sludge, varnish, all of these oil degradation products and things that are created in oil once you exert a little bit of thermal and mechanical stress to the fluid it causes a whole host of issues that I think many people are probably already familiar with. You know, certainly varnish and sludge can lead to sticky valves, increased bearing temperatures. They can cause premature wear due to what we call the sandpaper effect. And so there's a whole host of challenges with sludge and varnish. What I'm proposing here is that in addition to all of the other maybe little better known problems with varnish, is that they also are reactive. And so what does that actually mean? They can react with some of the formulation chemistry in your fluid. Predominantly, we first see these degradation products reacting with antioxidants, and so the premise here with my hypothesis is that if you are able to maintain an oil with a low level of degradation products, you should be able to extend the life of the oil. So that's kind of the hypothesis that I'll work through. What I will present today is a little bit about oxidation and how it creates radicals, and a little bit about the chemistry and degradation of varnishes, sludges, and other deposits that are formed. Talk a little bit about bleed and feed and some of the impacts that we see with these reactive products. And I'll end this with an experiment that we did that where I tried to at least conclusively show that there is a reactive nature to these oil degradation products here as well. So, all right, so without further ado, we'll get into this. To start off with, why do we care if oil degradation products are in fact reactionary? And I think the main reason is that if you have oil degradation products, varnishes, sludges in your fluid, and it's shortening the life of the oil, then that really is, there's a pretty solid economic impact that it can have on your bottom line. So I have a couple just quick case studies to review this, and I think the first time that this really became really evident to me was many years ago. I was working on a system that on a large ship that uses a controllable pitch propeller, and this is a pretty complex lubrication system that allows that both steers and propels large ships. And so in this case, the oil, it was an R&O oil, fairly unique chemistry. There was also a little bit of an EP package in this as well. But the oil was changed every time the acid number hit 0.2. And so a brand new system, the ship just fresh out of the dry dock, the oil lasts for 5 years. They change the oil out. The next charge of oil lasts for 3 years. And then the next charge of oil lasts for a year. And so clearly there was some concern that, you know, right off the bat, this oil, they should be lasting a long period of time, and now it looks like that, you know, there's a half-life. Every oil change, the product, the life of the oil is basically cut in half. And then what was revealed is that there was just no maintenance done whatsoever in between oil changes, and basically they were putting in nice fresh new oil into a pretty dirty system with lots of deposits. And so this was maybe the first time that I came across this. A more recent case study in a large frame gas turbine that the oil was really, you could see, clearly at the end of its life. Typically in turbine oils, when the antioxidants or the oxidative stability measured by RPVOT gets down to 25% of new fluid levels, that typically is a sign where the fluid's reached the end of its life. And so you can see here the antioxidants, in this case the phenolic antioxidants, 28%. We're getting pretty close to the end of the life of the fluid. The varnish potential, measured by the MPC, is fairly high. 58, I would say, is certainly in the critical range and is somewhat alarming. Foaming characteristics, in a turbine, typically when you have foaming of greater than 450 milliliters, then that would also be considered condemning. So even RPVOT was approximately 25% of the new fluid. So in fact, if we compare to the new oil, you can see the new oil had about an RPVOT of 1,600 minutes. So in this case, gas turbine, they dumped the old oil, recharged it with brand new oil. 1 week after the oil change, the phenolic antioxidants are at 74%. And the MPC is also rising and is much higher than should be expected after a week. Foam levels are higher, even the RPVOT has gone down. So in this case, you can see that the gas turbine, the plant did no clean out of the reservoir, flushing of the system, and basically we're dumping a fresh oil into a pretty dirty system, and you can in fact calculate how much it costs to make this whole oil change. It's not inexpensive, And if you consider the condemning limit is when the antioxidants are at 25%, right now we're already at basically 1/3 of the life. We've already depleted 26% of the initial antioxidants in the first week. So 1/3 of the life of the oil is essentially gone. And there's a quantifiable number you can actually put to that. The cost of not decontaminating your lube oil system between oil changes. So I think this is one of the reasons that we wanted to better understand this and study this a little bit more. One analogy that I often use is that you wouldn't want to take a bath in a dirty bathtub, and clearly it does not make sense to put brand new, nice, fresh turbine oil chemistry into a dirty system, especially when we see there are reactionary byproducts as well. All right, so a couple just quick case studies here to start things off. We'll talk a little bit about oxidation. So now I'm going to see if I can kind of prove out this this theory that these degradation products are in fact reactionary. I think you'll see here there's lots of observations we have, and theoretically there should in fact be the creation of radicals or these reactionary products as the fluid degrades. So if we just look at oxidation, which is the predominant mode of aging and failure for most industrial oils, if we look at just the basic chemistry behind oxidation, you can see all of the various different products that are formed. Many of these are in fact radicals. Free radicals are typically unpaired electrons that have a very, very short life. In normal oil analysis, you're not able to identify a lot of these. Some of these radicals are more stable and can actually reside in the oil for an extended period of time. Some radicals are so stable that you can actually measure them with some used oil analysis tools like infrared analysis. But in most cases, free radicals have a really, really short life. So one way of determining whether or not there are in fact free radicals, or this is just a theoretical academic exercise here, can you actually measure free radicals in oil? Well, there's a technology called the electron spin resonance, which is it's used a lot for measuring radicals in other sciences. And essentially what you're doing is exerting the fluid to a very high magnetic field. If you have an unpaired electron, you are able to excite that electron and essentially have a method of very quickly measuring that. So there's a nice example here of a new oil, and this is an engine oil, obviously, that we see the number of miles. And as you start to age the fluid and there's more miles on the fluid, you see at 6,000 miles, there's clearly some free radicals here that are able to be detected. So free radicals do actually exist beyond the academic exercise of understanding the process of oxidation. They do actually exist in oil. So let's talk a little bit about some of the deposits that we typically see in lube oil systems and understanding whether or not those may be reactionary. So in order to do that, we have found that there's a lot of value. One piece of advice that I'd like to share that we always discuss with our customers, anytime you ever have an opportunity to get inside your lube oil system during an outage, it represents a tremendous opportunity to see what is going on in the system. Unfortunately, in most cases, oil is, you can't actually see lubricants working and functioning. You can't see the wedge that it builds to maintain moving parts or separate moving parts. During outages, and when you have an opportunity to get inside a system, photograph a system, make observations, that there's all sorts of things that you can detect. And often, if there's accelerated oil degradation, you'll find the evidence of that through deposits that are in the system. And these deposits can come in a very wide range of different shapes, sizes, consistencies, colors, but if you have the ability to capture and collect a deposit, there's a lot of value that can be derived from analyzing that. And certainly test oil has a sophisticated analytical program to basically dissect and determine the chemistry of the various different deposits you may find. Typically, when you are doing deposit analysis, we like to think of this as a method of extracting deposits either from the oil or ideally you're able to extract deposits from the oil and actually have a physical deposit from the system. And from that, once you have gathered those samples, you want to understand the organic and the inorganic constituents that make up these deposits. So in the lubricant, elemental spectroscopy is a powerful tool. Infrared is also a powerful tool to look at the organic species. FTIR, infrared analysis, is also a very, very good tool to look at the organic components directly in deposits as well, and sometimes if you can couple that with XRF and other tools, you can do a lot to at least categorize the organic makeup and the inorganic makeup in some of these sludges, varnishes. Well, so that's fairly interesting, but I think even more powerful than that is that once you're able to extract the chemistry out of these deposits, in many cases, you can actually go back and determine actually what the source of this chemistry is. So, for example, this little glob you see on the left-hand side of the screen, this is something that we would refer to as a thermoplastic. It's a really cool type of deposit that if it's cool, it's solid. If you heat it up, it will melt and turn into a liquid, but this solid piece here, if you actually just drop that little piece on the floor, it could actually shatter like glass, and it really behaves like a thermoplastic. This is a type of deposit chemistry that we typically see, for example, in spark-derived lubricant deposits. If there's a very high amount of spark discharge, it would make this fairly unique chemistry that we haven't seen from other modes of degradation. So just to let you know, this is a powerful tool to not only say we have an organic deposit that's come out of the fluid that looks and behaves like a thermoplastic. Well, we also now know that it's derived from spark discharge, and there are known ways of being able to remove spark discharges that may happen in your lube oil system or in your filter system. So it actually allows you to go back and correct some of the root cause of this. So just quick overview on what we do for deposit characterization, but based on this, we have looked at many types of deposits in the field. And so I have a couple different examples here. Here's a bearing sleeve from a CO2 compressor, and if you look at the organic components of this with infrared analysis, you can see some fairly interesting things. So first of all, just a quick overview of infrared analysis. This is just a tool, a very useful tool to look at the molecular fingerprint of the oil, or in this case of the deposits. And essentially what we're looking at here is the chemistry on the x-axis and the amount of chemistry on the y-axis. And if you are not an infrared spectroscopist and are just looking at this, you can just compare these various deposits and see, well, we got a little dip there, matching. The red line is dipping at the same spot as the black line. You can get an idea that there's a lot of similar chemistries going on here. So some of the predominant chemistries we see in this particular deposit, we have some phosphates, some esters, and we have some water. And it doesn't look like a watery sample, but it's amazing. Almost all deposits that we see show some evidence of moisture. Moisture is, of course, can be a reactionary product and can, in fact, accelerate oil degradation. So, in fact, this is suggesting that there is some reactionary components in this deposit here. We look at another example. This is in an old steam turbine in a waste incineration plant. There's a lot of external contaminants that can migrate into the fluid here. Lots of deposits that we saw on the bearings. Elevated MPC patch as well. The ultracentrifuge showed some high level of deposits. At the chemistry of these deposits, lots of acids. Esters is a form of degradation, but these carboxylic acids, if you go back to the process of oxidation and all of the different byproducts that are formed, carboxylic acids are a key component that can certainly cause accelerated fluid degradation and can act as a reactionary body. Another example here, this is in a methanol compressor train, lots of deposits on the bearings, and sure enough, a very, very high amount of acids in this particular deposit. Lots and lots of acids and can in fact be reactionary. Next example here is from an ammonia compressor. This is a fairly unique chemistry that we saw, and we've seen this in many ammonia compressor applications. When ammonia migrates into the fluid, there is an opportunity for that ammonia to react with oxidation products, with oil degradation products, and form a fairly unique chemistry. And what we see here, and again, infrared spectroscopists will look at this and see a couple little doublets here that suggest that there is a primary amide chemistry that's formed. Essentially, it's this reaction of acids, oxidation products, and ammonia in the fluid. So this is interesting because not only do we see this in ammonia compressors, sometimes we may see this in steam turbines when you have steam that may accidentally leak through a steam turbine oil. Some of the chemistry that's used to maintain steam can decompose to form ammonia. So it's another potential source for ammonia to get into the fluid. The interesting part of this chemistry is that you can have all sorts of deposits, and if they are an amide type deposit, you may not actually see an increase in MPC values. So this is a reactionary product here that actually is hard to detect and predict through normal oil analysis. So it's, again, a pretty powerful tool to be able to identify what's causing this, so you can change both your contamination control program and also your condition monitoring program to be able to accurately detect this and predict whether or not this will become something that can impair the reliability of your plant. All right, final example that I have. Basically, I just like showing this example because we have a great video that goes along with it. But here you see lots and lots of water mixed with oil can sometimes create some fairly unique monsters. So this is almost a whole nother species that certainly looks, so just visually this thing looks like it's reactionary, and you would not want to have that in your lube oil system. So anyway, so you sometimes can get these fairly interesting reactions to make some just pretty interesting gooey substances like this. All right, so we are theorizing here that these deposits are reactionary. We have some observation that there are, in fact, some reactionary chemistries in the fluid. Here are some pretty interesting results, I think, from some bleed and feed experiments. So in bleed and feed is typically a maintenance practice to try to increase the concentration of antioxidants or other additive chemistry in your oil without having to do an oil change. In many cases, there's a certain percentage of your lube oil system that may be dumped. You may dump 5% or 25% of your system and replace it with 25% of new oil. So it's a practice that's been in use for a long time. This is some data from 7 different bleed and feed results. And so what we've done here, we have 7 different case studies. We have the phenolic antioxidants before the bleed and feed, and based on the percentage of bleed and feed, if it's a 10% or a 30% bleed and feed, you can, through some pretty simple mathematics, estimate what the actual phenol should be after the bleed and feed. And then we actually have what the actual phenols were. And as you see, in a lot of cases here, the estimated amount of antioxidants after the bleed and feed is in fact lower than what you calculate. And well, I think one of the key reasons why this is because there are some reactionary products in the oil that when you put these fresh antioxidants and this fresh fluid into a dirty system, well, some of those fresh antioxidants are being decomposed and reacting with some of the reactionary bodies in the system. So what I've done here on the right-hand side is I've charted the effectiveness in bleed and feed versus the bleed and feed percentage. And it's interesting that as you do a higher and higher bleed and feed, in fact, at this case, 30% bleed and feed, we estimated that the phenols after a 30% bleed and feed should be coming in at 38%. And in fact, we were really remarkably close. So conversely, at a 10% bleed and feed, it was significantly lower. So it's pretty interesting to see that there seems like there are reactionary products in the oil, and however the higher percentage of bleed and feeds you do, at some point it kind of it neutralizes, or the reactionary products that are in the oil have reacted, and then your estimated bleed and feed effectiveness is in fact significantly increased as you gain in concentration. So anyway, I thought this was interesting data. It's still not proving that degradation products are reactionary, but I think it's some good observations here that, again, are strongly suggesting that they are. And again, we have a couple case studies here at the very beginning, and also with these bleed and feed examples where we are certainly observing that fresh antioxidants may be more quickly consumed when introduced to in-service oils or into a dirty system. And so certainly if you have a lot of reactionary products in the oil and you're trying to extend the life of it through bleed and feed or an additive replenishment, the effectiveness of that is going to be significantly less. And then also the higher the percentage of bleed and feed, the more effective it is. All right, so we're moving on here to the laboratory world, and I'm going to show some data on us trying to better understand some of these reactionary components. So what we're doing here is we're looking at the antioxidant levels. So in this case, we have I think this is 40 used oil samples that we have in the laboratory added a certain amount of antioxidant of raw antioxidant chemistry to 40 different in-service oils. And then what we can do is, based on the ruler test, which is measuring the effectiveness of the antioxidant concentration, we can guess or predict where these antioxidant levels should be. And again, here what we've done is converted the antioxidant, instead of looking at a percent of new, which you may see sometimes in ruler tests, we've converted all this to an antioxidant concentration. So here we have a whole bunch of samples that we've added antioxidant to in the lab, and this is where we expect the antioxidants to be after the addition. So somewhere between 0.5 and, say, 1.5%. Here's the actual measured amount. So this is very interesting results. So in some cases, higher than one would expect, and in some cases lower. So and then we just have a line here that's kind of measuring the difference. But you can certainly see that there's some antioxidant synergies happening. So in these cases in the middle, there's minimal synergy that we would see. But in some cases, you can in fact add some antioxidants that have a synergistic effect and essentially suggest a higher effectiveness or activity of antioxidant chemistry than you would expect or predict. So, which is what synergism is. And then in this case, we have some anti-synergism happening. And there's also, since we're dealing here with all in-service oils, a lot of this can be explained by reactionary products that are in the oil that lower the effectiveness of adding fresh antioxidants to this in-service oil. So you see we have several examples here. All right, so that's one lab data here, and so ultimately we wanted to do an experiment that could really definitively prove that these degradation products are in fact reactionary. So what we did is we determined the antioxidant levels of a whole bunch of in-service oils. They all had high varnish potentials. So in this case, all of the MPC values were all over the all greater than 40. We measured the antioxidant chemistries, both the amines and the phenols, with a ruler, and then converted that to a ruler concentration just to make it a little bit easier to read and see the data. And a known amount of amines and phenols were added to each sample. Then what we did is we filtered the oil. We removed all the degradation products. The MPC values were less than 5 after our filtration process, and repeated it. So theoretically here, our premise is that if in fact we add fresh antioxidants in the lab to clean oil, you should expect a higher effective rate. Okay, so let's see what the data looks like. So here we have 3 samples. We have the amines here in blue, and the phenols here in brownish orange. And so you can see these are the 3 samples of amines and phenols based on the concentration. We converted this to a concentration. And now we're going to add antioxidants to it. Boom. You can see very effective amount of both the phenols and the amines and the phenols went up across the board here. Now we're going to take the same sample, filter it, remove the degradation products, and do the same thing again. And what do we see? In fact, we actually do see some effectiveness here. So in this case, we actually saw a 44% improvement in this fluid's ability to not react with phenols when we added. In this case, a little bit of impact on the amines, but a pretty significant impact on the phenols. Sample number 3, a 14% increase in effectiveness in adding amines to the fluid. So that looks pretty convincing. It suggests that, in fact, if you remove oil degradation products, that in fact you can, you're removing some reactionary bodies and adding fresh antioxidants to the in-service fluid, you should increase, you should have some more effectiveness. Unfortunately, in the world of science, not all data is conclusive. So here we have the exact same test process with samples 4, 5, and 6. And essentially, we saw no improvement. So again, here we went through, filtered the sample, added the same level of antioxidants. The effectiveness was essentially unchanged, maybe a little bit lower in sample 4, but essentially unchanged. So we went through, did this effort to try to conclusively prove this. I would say our at least laboratory experiment here didn't conclusively show that that all degradation products are in fact reactionary, but we certainly think that some oil degradation products are reactionary. Certainly our laboratory test data is suggesting that. Observationally in the field, we see this all the time. So if you have you have a dirty system and you're adding fresh lubricant to a dirty system, you should expect that life of the oil to be pretty significantly impacted. And so at least observationally we see that. One of the other key points here, so we're saying some oil degradation products are reactionary. In reality, there really are hundreds of different types of oil degradation products. clearly some of them are not reactive as well. In terms of measuring oil degradation products, the two key tests that we talked a lot about here, infrared analysis, a membrane patch colorimetry test, both tests that Test Oil does, and can be very effective for measuring oil degradation. And ultimately, removing oil degradation products really should have a positive impact on extending the life of the oil. And for you chemistry geeks in the audience here, just a little chemistry joke for you. All right, so that's a quick summary, and I think we have a little bit of time there. If there are any questions, we may have a little bit of time for some questions here as well. So, Carrie, maybe I'll turn this back to you, and you can see if there have been any questions that may have come in.
Yep. Can you hear me, Greg?
I can. Yes.
Okay. Sorry, I had you on mute. Yes, we have a couple questions. So I'm going to go ahead and see if I can decipher through these. So the first one is coming from Steve, and it looks like Steve might be in the Dallas area. And his question is, what do you recommend are the best test methods for monitoring oil degradation?
All right. Thank you, Steve. I think that we talked about the, so I think the first key point in designing your condition monitoring program is understanding how your fluid is failing in the application, and then really designing your testing program to detect how your fluid is failing. So in the case of turbines, if you are using a membrane patch colorimetry test to look at the creation of soft contaminants and varnish components, that's one of the primary failure modes of turbine fluids, and would be certainly a very appropriate test to look at for monitoring the health of turbine oils. If you're looking at other chemistries, some hydraulic applications, maybe phosphate ester fluids, acids may be a key form of degradation product, so a total acid number may be an effective way of measuring oil degradation products. And certainly if you are dealing with any organic additive components that you want to monitor and measure, infrared analysis can also be an effective tool. A ruler test is an effective way of monitoring antioxidant depletion. So, thank you. Good question, Steve.
Okay, I am getting more. Here's another one, and this is from Jim. It looks like California somewhere. Is there a way to remove varnish from the oil?
So oil, yes, good question, Jim. I think there are many different technologies available to remove oil degradation products. The one key thing is that if you have a high MPC level or a high level of varnish in the fluid, that's not necessarily a condemning limit. It doesn't necessarily mean that you have to change your oil. It's just like if you have a high particle count, there are filters that you can put on the system to remove those contaminants. And same thing if you have a high varnish potential. In most cases, what you want to try to do is match the varnish mitigation technology to the actual application. So if you have a colder oil, things like, and you have oil degradation products that may be in solution, you can get really effective depth media filters or electrostatic technologies to remove some of those oil degradation products and varnishes. If you have hot oil and organic degradation products that are dissolved in the oil, they're all in solution, then you need to look at more of a chemical type filter, ESP, or a resin-based type filter that can actually remove those oil degradation products while they're actually in solution. Good, thank you, Jim. Good question.
Okay, I have two more for you, Greg. This one is coming from Salvatore, and he is in Georgia. What might be the differences in the identity of the oil degradation products in oil samples 1, 2, 3, 4, 5, and 6? So this must be referring to one of your slides.
Yes. Good question. So that is some of the challenges with us doing, at least in this case, some of the examples or some of these experiments in the lab is that we were essentially trying to show the reactive nature of these degradation products, but had limited sample to actually do root cause analysis and deposit characterization of these actual deposits. So in this case, we had 6 samples, all with MPCs. In this case, they were all turbine oils. They were used in a wide range of different applications, and so they all had MPCs greater than 40, and the data is suggesting that samples 1 through 3 had some reactionary products that are in the oil, whereas samples 4 through 6 did not have reactionary products, or the degradation products were not at least impacting antioxidant chemistries. So we did not do the analysis to conclusively determine this, but I would guess that there are, if you have some spark discharge, or I showed the picture of this thermoplastic type material, we find that is actually not as reactive as some other more radical or proxy type radical degradation products that we would see that may be derived through oxidation. But again, we did not conclusively test for that in these 6 samples. So good question, and I think and very insightful question, and I wish I had a conclusive data to answer that for you.
Okay, I have one more for you, Greg. This is from Eugene in Florida. Eugene is asking if you can suggest a way to remove sludge and varnish from a system between oil changes.
Okay, so I think that's a very important point, and I think one of the key points of this webinar that I am hoping that made it through to you is that there is a lot of benefit in decontaminating a system between oil changes, and putting fresh oil into a dirty system is just not good for anybody. It's not good for the oil supplier because their brand new beautiful formulation and this great product that's been generated or that's been made just for your system, suddenly a week after it's been put in your dirty system, it has lower effectiveness. It's not good for the end user. So decontaminating a system between oil changes provides a tremendous amount of value. That gets us to the world of flushing, and there's many different types of flushing processes available. One very common mode of flushing is referred to as high velocity flushing, and typically high velocity flushing allows you to you're flowing fluid through the system in a turbulent way 3 to 4 or maybe even higher than that times the normal velocity of the fluid, and that allows chunks and debris and other things to basically be pushed by the fluid out to collection filters or strainers. And so that's really effective at removing broken components or flushing welding slag out of a brand new commissioned system. Very effective way of removing dirt and debris, but it's not so good at removing oil degradation products. So to remove oil degradation products, some of these varnishes and sludges can be challenging to remove, and varnish over time can cure almost with heat, can cure onto metal surfaces and can be really challenging to remove. Typically there's 2 different methods that people use to remove those. One is through a chemical flush, and in a chemical flush you're adding chemistry to the fluid to allow some of those contaminants to be scrubbed off the walls and suspended in the fluid. So in many cases you are using a dispersant or a detergent type cleaning agent. You will allow that to circulate in the oil for maybe up to 48 hours. It does a really effective job at loosening all the dirt and suspending all the sludges and varnishes in the fluid, and during an outage is an effective way at pretty quickly cleaning up a system. The challenge, of course, with putting detergents and dispersants into a turbine oil is that this is not desirable additive components for turbine oils. And because these components are so polar and so active, they're actually able to get behind this really stuck on, or this varnish is really stuck on the surface. It's so polar it can actually get behind there and loosen it off. The challenge is that when you drain this chemistry and you drain all the fluid out of the system after your flush, all of these polar components are still hanging out on the walls in the internals of the system. And so it's really challenging to try to remove that. So typically you'll have to do some flushes to try to rinse some of that off, and you still may not be able to remove it all. And the challenge then is that some of these chemistries can, if they're still residing in the oil, even at a really small concentration, it can impair the new charge of fluid. So you may have a lower water or demulsibility characteristics, for example, in your new charge of oil. So another technique to remove oil degradation products, varnishes, sludges from a system, is putting a solubility enhancer into the fluid. And if you design this correctly and have a solubility enhancer that's added a few months prior to your outage, it's often coupled with a varnish control technology, and the combination of the two allows varnishes to dissolve back into the oil and then be removed through a varnish mitigation system. So it is not as quick as adding a dispersant to the fluid, but it's inherently safer because you're not adding any incompatible chemistries to the in-service oil. So those are a couple different methods that you would consider, but the bottom line is there is a tremendous amount of value in decontaminating your lube oil system between oil changes.
Greg, I have several more questions, so I'm going to keep going through these if we can. I might have to leave some of them for you to answer via email, but let's try one more. This is from Anthony, and Anthony is asking, how were the samples filtered in your experiment? Can this same filtering be done outside of the lab on oil in our reservoir?
Yeah, so I've done my best to be as vendor neutral as possible in this, but I will just, a little plug on Fluitec. We've developed a varnish mitigation technology that we refer to as ESP, electrophysical separation process. So it's a varnish mitigation technology that we install on systems, and in our experiment what we did is scale this down to a laboratory type experiment. So we're essentially running hot turbine oil through a column of the media that we use, and we're able to simulate in a laboratory what we would do in an actual system. But certainly, yeah, those would be, this is a technology that we also have commercially available as well.
Okay, should we try one more?
Sure.
Okay, Francisco is asking, in the results of an analysis of engine oil to a high level of gas oxidation and nitration reported. Hopefully these results when the machine was stopped a long time. What risks are there in the machine? You understand that?
Oh, so I think, I'm not sure if maybe repeat that again, Carrie, and I'll see if I can, I think you may be referring to the if there is risk in an oil that's had engine oil that's had accelerated oxidation and nitration. If that oil sits in the engine for a long period of time and is not, does that have other risks associated with just residing in the engine for a long period of time?
Right.
How I interpreted that.
I believe that's the question. Yeah.
Okay.
Yes, it seems right.
So in engine applications, there are certainly some degradation products that that could be fairly acidic in nature. So engine oil chemistries are designed to have dispersants and detergents that keep all these degradation products in suspension. But there certainly is if you have a severely degraded engine oil and it's just residing in the oil, you know, we see this in laboratory tests. If you do an engine oil test and then leave that oil in for a long period of time, you do risk corrosion of some components in the engine due to some of the acidic nature of some of the degradation products and some of the combustion products. So there is a risk of some corrosion happening. There's also a potential for some of these dispersants to, I call them, they will crash out and essentially no longer able to suspend and hold all of these combustion products and soot, and so you may end up with, when you actually do change the oil out, you may have pockets of sludge and varnish that normally would be removed in an oil change with the dispersant chemistry that may no longer be so healthy. So I hope I interpreted the question right, and I hope that answer may be of value as well.
Okay, let's do another one. This is from Pablo. If MPC doesn't always detect, is it amide products or amine products? What would you recommend to detect these? Ultracentrifuge? Question mark.
Good question. So this is actually, I think I used this example in a previous webinar that we've done before here, Carrie. But this has been a fairly interesting phenomena, and there are a few modes of degradation that we find that deposits can happen, sludge can be created, and the MPC is not, doesn't predict this. Certainly that can be problematic. So in the case of primary amides, there's a couple things to be aware of. The first thing is that there's two necessary components that you need in order for an amide to be created, and so I'm just going to pull a slide up here, but one of them is carboxylic acids, oil degradation products. The other is ammonia. So if you have both of these under the right conditions, they can form this sludgy material that comes out of the oil really quickly and doesn't allow MPC to be measured. So what can you measure in this case, and also what can you do to to correct and predict or eliminate this potential mode of degradation? So ammonia, you just may not be able to do anything to impact ammonia ingression. If you have a screw compressor, an ammonia screw compressor, ammonia is just going to get into that oil. There's nothing you can do about that. In the case of a steam turbine, if there's steam chemistry that may migrate into the in-service turbine oil, there's nothing you can do to eliminate steam leaks from ever happening. Carboxylic acids, however, are a component that you in fact can measure in an oil analysis program, and in fact this is a chemistry that you can effectively remove. So carboxylic acids are a form of oxidation. It's an oxidation end product of oxidation, and if you have these carboxylic acids, you can in fact measure their presence in infrared analysis. If you work with a lab that has sensitive infrared capabilities, they can in fact 1714 typically is where this chemistry will pop out, and you can so that can be one mode of measuring this. There's also varnish mitigation technologies that you can do to actually remove these degradation products. You may look at changing your oil frequently, much more frequently, or doing bleed and feeds more frequently to ensure that this level of carboxylic acids doesn't accumulate. And if you can eliminate these degradation products from being in the oil, then you're essentially eliminating this potential pathway for this primary amide chemistry. So that's a couple things to consider here, but this is just a good example of why it's important to do, instead of just assuming sludge is sludge and all varnish is the same. It's actually, I think there's a lot of value in in ripping apart this varnish and understanding the chemistry so you can make some more proactive decisions in your maintenance program to, to eliminate some of these modes of degradation. Very good question.
Okay, Greg, this is the last one, and this is another question from Pablo asking, except for phenolic AO, where do the aromatics come into the in-service oil?
So aromatics could be a form of gas that could migrate into the oil. You may, depending on the formulation, you may have some very, very small amounts of aromatic content if you're using a Group 1 base stock that could be in the oil. But typically, if you see a migration of aromatics into the fluid, it's indicating some external contaminant that is getting into the fluid. So you may even see some cleaners that could get into the fluid. But typically that's going to, especially if you start to see an accumulation of that's a contaminant that's migrating, likely due to processed gas or another contaminant as part of the process that's getting into the fluid.
Okay, well, you sure talked a whole lot in that last hour. Thank you so much, Greg. You are so full of information, and I know all of our attendees really appreciate learning from you. We love having you as a guest speaker. Just to remind everybody, I will send you all a copy of the recording of this webinar probably in the next few hours, along with a survey. So if anyone has any additional questions, you can ask them through that survey, and we'll get the answers for you. So thank you again, Greg, and everyone, you have a great day.
Thanks so much, Carrie. Thank you, everyone, for listening in.
All right, take care. Bye-bye.
All right, bye-bye.